Hey everybody! Today we're going to be going over a very common interview question often asked by Facebook called the longest substring without repeating characters. And the problem goes as states. Given a string, find the longest substring without repeating characters. Note the two keywords here, length and without repeating characters. So we're returning the length of the longest substring, and it cannot have repeating characters. Let's take an example of this problem. Given the input PWW, we can see that the two longest substrings without repeating characters are WKE and KEW. We see that extending either substring, either side, would result in it being invalid because it would have a repeating character. Therefore, the output would be the length, or 3. Given another example, input BBB, we can see that only the substring B exists without repeating characters. So therefore, the output would simply be 1. So let's go over some approaches we can take for our problem here. And the first thing you want to do in an interview when you're thinking about the solution is to approach it using brute force. And oftentimes, suggesting or using brute force can lead you to the correct answer. So in this case, let's think about a brute force solution. So given our string here, let's say it's this string, our brute force solution can be to generate each possible substring, and simply check, 1, if they're valid, if they don't contain any duplicates, and 2, if they are valid, if they are longer than our max valid string. So in this case, we can check K, then we can check KW, starting from the first index, then check KWW, then check KWWK, and so on. And for each check, we check whether or not there's a duplicate character. So there's no duplicate. We see there's a duplicate character here, so we no longer check if it's the max, and we keep going until we generate each possible substring. And in this case, the time complexity would be O of n squared, because we're checking for each starting point, we're checking every other character. But because we're looping, the space complexity is just O of 1, or constant. So can we do better? So let's think about some approaches that we might take to optimize our solution. The first thing we can think of is in the previous solution, instead of generating each possible substring, we can simply stop checking additional lengths or additional substrings starting at a certain point when a duplicate character exists. So for example, in our previous solution, we would check K, KW, and KWW, and we would keep going after that as well. We would keep going, we'd check the rest of the string. But it turns out that once we see a duplicate character here, the next character will definitely always have a duplicate. So instead of continuing to check, we can simply just stop here and move to the next point. So now we can check W, W, W. We see here another duplicate character, so we stop at this starting index. And we know we can move on to the next index, starting index, because no longer substring will be possible from the current index once a duplicate is found. So starting at K, there will exist no longer substring without repeating characters than simply KW. So in this case, we can build in our code a functionality where if we see a duplicate, we just break out of that particular for loop and continue on to the next string. So what would our time complexity be in this case? Well, since there's only 26 characters total in the alphabet, at least in this problem, that we can assume, we can see that for each starting index, we'll only hit 26 characters. So our time complexity would actually just be O of quote-unquote 26n, or O of n. And our space complexity will be constant because we're not using a data structure. Actually, more on that. So how do we keep track of what character is currently in our check? How do we know that we've encountered a duplicate? So in this case, we can either use a set, which we can think of when we need to find something that doesn't have repeating characters or repeating strings and so forth. Or we can use a character bank, which is an array of 26 characters that use the ASCII value to keep track of what is currently inside of the value. So I guess the space complexity would be O of n, because the set would first be a data structure and could contain all the possible strings. Well, the argument here for it being constant is that since there's only 26 max characters, we know exactly how many characters that the set will contain at all times, or the maximum number of characters it will contain at all times. So we can argue that is O of 1. Can we have a different approach to the problem? It seems like O of 1, or O of 1 space complexity and O of n time complexity is already really good, but is there another approach? So now we're going to go over a very common technique used for data manipulation or string manipulation called the sliding window technique. The sliding window technique. And this technique involves using 2 pointers, so 2 pointers, to keep track of a window in our substring. So with these 2 pointers, we'd have a left and a right delineating the border of the substring. So a left value of 0 and a right value of 2 would indicate the first 2 characters. So let's say it's A, B, C, then 0 here, and then a right pointer actually would be the first 3 characters. So it would delineate this substring here. And what we could do is we could shift the window once we see a duplicate using the previous strategy. We can shift the left window 1 to the right and keep all the characters, at least so far, inside of our window. And this would remove a lot of redundancy by resetting our entire window. So in the previous problem, what we were basically doing was, let's say we have the string ABC, ABC, BB. We would be sliding our window, so A, then B, then C, and then once we see a duplicate, we would reset this whole window and start over at B. In this technique, we would actually avoid restarting completely and simply maintain our current string, but shift this one over to the left, or to the right. Shift the left pointer 1 to the right, and check again to see whether or not this window is valid. In this case, the complexity, the time complexity would actually be O of n as well, and the space complexity, using the same argument as before, would be O of 1, because there are only 26 characters total that can possibly be in our data structure at one time. And going over this further, so if after we shift the left pointer 1 to the right, we'll check whether or not this window is valid. And if it's not valid, we'll continue shifting it until our window is valid. So in this case, like we mentioned, time complexity O of n, because we're just traversing through each element. It wouldn't be O of 26n, so it'd be slightly faster, but not significantly. And the space complexity would be an auxiliary O of 1. So let's go ahead and take a look at what our sliding window technique algorithm looks like on pseudocode and illustrate it using 2 pointers and a nice pen and pencil. So I've gone ahead and illustrated here what the steps are. So the first step is to add the character located at the right index of the input string into our set, and we check whether or not it actually exists. If it doesn't exist already, so if the character doesn't exist in our set, we go ahead and add it in, we iterate our right, so we expand our window, and we make sure to update our max point. And our max point is updated based on the current size of the longest substring without repeating characters. So it would be the right index minus the left index, assuming that the right index has been iterated. However, if the character does exist, we need to shift our window our window is no longer valid from that current starting point. We've reached the maximum potential. So we need to remove the character at the left pointer from the set and iterate it to check the next starting point. And we repeat this process until the right index, and there's actually a typo there, it's just the right index has reached the very end of the input. So once every single character has been put into the set successfully, then we can stop the iteration. So let's go ahead and illustrate what this looks like. We'll go ahead and maintain 2 pointers. So we'll have a left pointer and a right pointer. We'll use green as right and blue as left. And we'll go ahead and maintain our maximum, which is currently 0, and our set, which is currently empty. So our first step is to insert whatever character is at the right pointer and update our max and add it into our set if it's possible. So our next step here would be to KE, and our right pointer, after inserted, our set would now have P, and our right index would now be iterated to W, left pointer to P, and our max would now be right minus left, which is 1. Okay, great. On to the next step. So, alrighty. Now let's try to insert our right pointer again. So we see here that our set does not have another W, so we can go ahead and add it into our set. We can go ahead and iterate our right pointer. So now it's pointing at another character. Our left pointer remains unchanged, and our max now is actually 2. So our current substring is PW. Now, this is where it gets a little more interesting. So I'll go ahead and start back here. And we can see that if we attempt to add the second W into our set, we will see that it already exists, so it will return false. And what we need to do is go into this second body here where it says exists and remove the character at the left pointer. So we now know that any substring without repeating characters starting at P will not be longer than PW. So we need to move on from that. So now we can remove from our set the P. So now we just have W, and we can go ahead and shift our left pointer 1 to the right, and our right pointer remains as is, and our max remains unchanged. It still remains at 2. So let's go ahead and repeat this process, So now, if we still attempt to add this right character here, we still see that it's invalid. We still see that the set still contains it. So we need to repeat the process of removing the left point or shifting the window. So now the set is now completely empty because we removed this left pointer character. So now the left pointer is now pointing at W, the right pointer is pointing at W, the set is empty, and our max is unchanged. So our max here is still 2. Alrighty, so now that the set is empty, we can probably, and when I say probably, I mean definitely, we can definitely add in the character at our right index. So now our set has a W in it. Our max is still 2 because the difference between our right pointer, which is at K, and our left pointer, which is at W, is still smaller than 2. Okay, so we're almost done here. So now our pointer, so after iterating it, we need to add in the K, the character at the right pointer, into our set. So now our set contains WK. Our max is still 2. And we iterate the right pointer, and the left pointer remains unchanged. Alrighty, so we are now at the end here. Okay, so let's go ahead and move on to our next step. So we have P, W, W, K, E, and we need to check whether or not we can add in our character at the right pointer, and we see that we can. So now our set is equal, or has a E now, and our max is now 3 because the difference between E and our left pointer, so now we first iterate it, so now it's actually one higher than the, or it's actually exactly equal to the length of the substring, of the entire string. And when we subtract it from our left pointer, we see that it's actually 3. And this hits our terminating condition because every single point on this input string has been added into our set at one point. So now we can terminate and we can return our max, which is 3. So now that we've illustrated this concept, let's go ahead and actually code it out with our nice pseudocode to the right as a reference. And we're actually using LeetCode to go ahead and test our answer, and it's what we base this question off of, so shout out to LeetCode. But let's go ahead and start. So first things first, you always want to check for edge cases on or during an interview. You always want to mention and oftentimes code in edge cases. So if the string is null, or if the length of the string is 0, and in this case it won't actually, if the length is 0, we actually account for it in the algorithm, but it's always good to sort of keep track of it. So we return 0. And I just realized I prefer to code it in Java. So I'll go ahead and do that again. Or the length is equal to 0. We'll go ahead and return 0 because no string exists. So the length is 0. And we'll go ahead and use our set. So we have a set of characters. Of a set of characters which will keep track of what exactly is in our sliding window at the moment, and it'll allow us to see whether or not the character already exists inside of the sliding window. And our terminating condition, so we have here repeat until right index, ignore the left index, right index has reached the length of the input. So we keep running while I should say we should define our pointers first. So we initialize them at the first character. And we also want to initialize a max, which we'll set to 0 for now. And our terminating condition is while the right index is still valid. So while the right index is still on a pointing at a character within our string. So while it's less than s.length, we keep going. And we see here that so let's go ahead and check whether or not the character at the right index is in our set. And the set has a nice function here. If we just do .add and we check char at right, if we do this, it will add it in if it doesn't exist, and we'll return true, and it will return false and not add it in if it doesn't exist. So we can just literally just put set.add in the body, in the conditional of the if statement. And if it is true, then we first iterate our right point, and then we check whether or not our max has been updated. So we do that, we check whether or not right minus left after iterating right. So it's important that we include this step before this step, otherwise we have to include a +1 there, and otherwise then we need to shift our window. So I guess this one I'll go ahead and comment. Go ahead and comment here. This is expanding. I guess you can't see it anymore, but it's expanding our window. And here we're shifting our window. So we need to remove the character at the left pointer from the set and iterate our left pointer. So we go ahead and do set.remove s.char at left. and then we iterate our left point. And I'll go ahead and put the iteration within this. So first it'll remove it at the left character, then it will increase it by 1. And that is it. It's very simple code, and this is why the sliding window technique is used in a lot of bit manipulation, or not bit, string manipulation, because it's very simple and it encapsulates a very significant idea of checking whether or not substrings are valid, or checking, sort of certain properties of substrings. And then here we return max. So let's go down here, hopefully run our code. Hopefully it works. Oh, I guess I have to sign in. Well, this code I know for a fact works. So thank you for watching, and I'll see you in the next video.